Hello, everybody. Michael, Mina, Dylan. Can you guys hear me?
Yes.
Good. Thank you. Hmm. Okay, let's see. That's me. Oh, wait. Hmm. Come on now. Okay. Gosh. I cannot even seem to get a stupid virtual background working. And I have my nose cam. Let's see here. This guy's smaller. This guy's smaller. Hmm. Let's see here. Let me go to share screen. Let's try screen two. Good morning, Nicholas. Were you here last Thursday?
I was.
Oh my God. I suck.
I didn't say anything. It's okay.
Oh, goodness. Okay. So, let me see. Who is Matthew Pham here? You're not Matthew Pham. You are. You're muted.
Yeah, I have to change my name. Sorry.
Your new name is Matthew?
No, it's my son's name.
Oh, okay. That works. That works. Good morning, Cynthia. How are you?
Hi, good morning.
And Diane, how are you?
Morning. I'm good. How are you, Professor?
I'm all right. I'm all right. I am thinking about just talking exclusively about the Poisoner's Handbook.
Cool.
It's actually a real fun book. I read it. Actually, I listened to it a bunch of times because I don't read anymore. I just get stupid audiobooks and I listen to them when I'm driving and other things like that. So I'm always going to be lying. I'm always going to be lying, saying, "Oh, I read this or that," but it's always an audiobook.
There's no shame in it, Dr. Terrell. Reading's hard.
Well, there you go. There you go. But I think that, if you got to have like science articles and stuff like that, and textbooks and things like that, I think it's actually better. I could be wrong, but I think it's actually better to have a physical book.
I like the physical books.
I,
Well, I'm a visual person. It's like I need to see the words to understand them. And to remember them.
Right. It's a kind of a, and now I'm trying. I got the virtual textbook for this class for this semester because I need to keep things sort of organized and contained and sort of like in some semblance of like scope, because I've always struggled with that too. So hopefully, there actually are a lot of copies of quantitative chemical analysis out there, a lot of used copies and stuff. So if you wanted to get one, you certainly could, of course. And I have several sort of editions. They've sent me new editions over the years. But Kareem's here now. We can start.
All right, party time.
Hey,
I'm
Kareem, how are you, sir?
I'm doing well. I
Good.
woke up early, so
I
had a
know.
cup of coffee too.
Excellent. Yay. I'll hide my political stripes here. I actually got criticized last year for having political stripes. So you guys can't see my cup and who I voted for.
Wait, on your soats or?
Yes.
Oh, funny.
Yes. Because, I just mentioned it, but it was just, people were so worked up about it,
Wait,
So anyway.
can you show us your mug or?
Oh, no.
Now
I
I'm
cannot
curious.
show you my mug. That would be a lot. Wait. I can't do it.
Except it's backwards, so it's a little hard to read anyway.
Yeah, you can't read that. It's backwards. You couldn't possibly read it.
Oh, wait, no, okay. I see.
Thank you for keeping it hidden, Dr. Terrell.
Yes, exactly. Keep those snowflake views hidden, man. Okay, so what are we gonna do today? So I was thinking about it, and I just want to use my stupid document camera today. And I'm going to go through and basically there's a homework due this Friday on statistics. Most of you have seen it all and done it all. Some of you have seen and done none of it. But I wanted to just talk about it a little bit. So I'm going to try to use my document camera here. So let's see how that works. Okay, that's going to be new share. Oh, wait, no. I'm not going to do it that way. How am I going to do it? I'm going to do it like this. Okay, this is my document camera. This is a cable going from my computer to the monitor you're watching on. But this is basically how I like to communicate with y'all today. So I want to try to boil down the statistics thing. And I don't know if I need to refocus this or not. Let's see. Whoop, there we go. All right. So I'm gonna risk repeating myself and getting into all kinds of trouble here. But I'd like to boil down statistics just a little bit for you. There's the realm of the theoretical, right, in which there exists, for our purposes, a Gaussian distribution. Right? And that Gaussian distribution has the form of e to the minus z squared, right? It's like, this is the general form, right? And z is the distance from the mean in units of 1 standard deviation. So let's say well, let's also even say that minus infinity is less than z is less than infinity, right? So this is like that's the domain of z, right? Okay, so this is e to the minus, this is a z here. This is the numbers. This is 2 for squared, right? And so what that means is that since it's z squared, this is always positive. And since it's minus z squared, this term is always negative, right? And so when z is equal to 0, this function is at a maximum. Right? And so this normal distribution function, it goes down like that on either side, right?
I think it's a little bit cut off on the bottom, Dr. Terrell.
Oh, thank you. I promise I will. There we go. So this is the probability of making an observation x, and this is x, and this is x equals mu here, where and then also when x is mu, z is equal to 0, right? So, and this is sort of the theoretical way that probabilities vary with, you know, with a value. I mean, there's lots of different examples in nature, I'm sure, and I someday I've got to learn a little bit more about statistics so that I can get a better grasp on like when to use a Gaussian distribution and other types of distributions, you know. But this is one way to do it. Hi, Van. You have amazing amazing background. You have
Jellyfish.
those jellyfish, right?
Yes.
That's awesome. I love it.
Thank you.
You're welcome. Thank you.
You're welcome.
So so this is basically all in theory, right? And what we actually normally have is normally we have data, right? I can say what we have here is just, you know, just data. We have no idea whether, you know, if we were able to replicate a given measurement, whether it would obey a Gaussian distribution function eventually, right? And sometimes there's no way to know, right? So what we have are data points. So we could have like one data point there, one data point there, maybe one data point there, right? And so like, and what we're going to try to do generally is we're going to try to reproduce, you know, we're going to try to get to mu. From the data points. So so if we just look at this little set of 3 points, and then there's this curve, right? Let's just say that this curve is the actual parent distribution from which these data points come. So, like, if we were to take a bazillion more points, they would eventually stack up and give us this P of X distribution. Right? We'd plot X here, and then when we get 2 data points, we'd stack them on top of each other like that, right? And then eventually we get the peak of the stack would be right here at X equals mu or Z equals 0, right? Etc. So let's just pretend now, but let's say we've only got 3 data points. And we're going to try to estimate mu from these 3 data points. So the way we actually do that is we say, well, there's X bar, right? We know how to calculate the average. And then there's S, the sample standard deviation. Right? And we're going to say, well, within what range are we confident to find mu? Right? We can't say exactly what mu is, but we can say within what range we are likely to find mu. And in order to do that, we're going to use a slightly different distribution function. We're going to use the t distribution. And so the t distribution, let me just ask a sort of a diagnostic question here. Is the t distribution broader or narrower than the z distribution? So what I mean by this is when the t distribution is going to make an estimate of where mu is, right? Based on limited data. Right? So who would like to make a, and even Cindy can answer. I open up the floor. Who would like to take a stab at whether the t distribution is broader or narrower than the z distribution?
Can I do it? Dr. Terrell?
Yeah?
I'll just try. I'm not sure. T distribution broader. I believe it should be broader.
Okay. And why? Why?
I just have a gut feeling, that's all, but I'm not sure if it's right.
Okay, all right. Any other gut feelings out there?
Were you saying that the t distribution was based on more limited data, Dr. Terrell?
Yes. Yes.
I think that would be if it's more limited data, I guess it'd be a worse estimate
Right.
for mu.
Right. Right. Exactly right. Exactly right. It is a crappier estimate, right? I mean, it's the best you can do with limited data, right? But it's not, it doesn't go all the way back to a theoretical distribution, you know? It doesn't actually tell you what mu is. It just creates some boundaries within which you can say, well, given these data, you know, 9 times out of 10, mu should be in this range, right?
Well, our standard deviation is going to get tighter as we get more data. So if we're kind of limited, I would expect it to be kind of diffuse.
Mm-hmm. So that I can't even ask permission here because I don't know how. But that is actually not true.
No? Okay.
So, but let's think about it a little bit, right? The standard deviation is there's basically 2 standard deviations, right? There's a population standard deviation, which we usually give the symbol sigma. And sigma refers to this Gaussian distribution. And then there's the sample standard deviation. This is population standard D sigma. Then there's the sample standard deviation. And that is normally given the symbol S. You know, There's the Greek letter and the I don't know, the English letter, whatever, the Roman letter, I don't know, the normal letter. Nicholas? Nicholas, are you there?
Yeah.
This is Greek, right? Sigma is Greek.
Yeah. So
So what is this Roman, or what is this? What is the normal letter? How do you distinguish it?
just an English letter.
English?
I don't
Okay,
know.
but it's used by everybody in the Western world, right? You know, obviously not by Arabs, and like you go like east of, you got like the Greeks, right?
Mhm.
From the Greeks eastward, that's a totally different alphabet, right? East and north, you go to Russia, and it's pretty screwy up there too. They write the R's backwards, and they got extra letters and stuff. Okay, so I digress.
Not sure what to tell you.
Okay, we'll figure that out. I think it's Roman. Let's say Roman. So we got the Greek letter mu. We got the Greek letter sigma and the Roman letter S, right? And now the thing about S is that S characterizes the width of this distribution, right? And so you can measure S over and over. And what will happen is, like, it's fun to do. You can do simulations of this, right? And I'll cook some up for you, right, in Excel sometime. And you can have you'll see that S will jump around. It will get smaller and larger, right? It'll never be negative because it's the square of a difference, right? But it's the square root of the square of a difference, right? But it will just fluctuate, right? If you have a limited number of values. Now, if you have a whole bunch of values, it will fluctuate less, right? Its value will be more accurate. So, but unfortunately, but we never know sigma. Really, we almost, I guess it's possible to know an estimate of sigma, but let's just say we rarely know it. Right. So in order to make an estimate of the value mu from limited data, we need a broader distribution function. And I don't really know how they did it, but I've gotten a little bit of a taste of it. It's not that complicated to go from a Z distribution to a T distribution. Okay, so the T distribution is just a little bit broader, right? It's a little bit flatter and broader. So this is the T distribution. And another difference is that the T distribution depends on the number of data points that you're deriving it from, right? So T belongs to, T is a universal distribution type that belongs to a number of degrees of freedom, right? And the degrees of freedom here is like, it's for normal cases, it's just n minus 1, right? If you're taking an average, it's n minus 1. So that's a sort of a weird complication, which I never ever want to get into ever. And I will blow ink like a squid if anyone asks me about it. And I will disappear.
Okay, let's ask him because I want to see this.
Okay. Here's how I blow ink. Uh, so so basically, what we can say if we have this type of information is we can say that we are we can define a confidence interval. And we can say that we are, say, 90% or 95% confident that the mean is in this interval. Right? So that means that roughly one time in 20, we will be wrong. And when we say that our value or when we say that mu is in a given interval. Confidence interval, CI. So, you know, and then the way you calculate the CI is fairly straightforward. Like it just, the CI is X bar plus or minus the appropriate value of T times the sample standard deviation divided by the square root of N. I'll use capital N here. That's the number of measurements. Let's say T, let's say 95 N minus 1 T. This is the, it's a number. It's just a number. You can calculate the number. It's just, I forget what the number is. Anyway, it comes from the T distribution, right? And it's the width around the mean that you have to go to make sure you get 95% of the area under the curve or 95% of the probability, right? It's a width in which 95% of the probability lies. And then S is the sample standard deviation. The one you calculate, right? So it's not really that, it's normally not that complicated to calculate, right? You just get T from the table, etc. Right? But it's really the first step into like can I actually say anything with the data? You know, can I actually make an authoritative statement given these stupid measurements that I've made? So that's I don't know. What is it, Cindy? It's stupid. No, it's not stupid. I'm just at a loss for words. Dylan, what do you think?
Yeah, you and me both.
Okay, all right. So, you know, I was thinking about this morning, and I realized that I am too old to teach statistics. I cannot do it. When I was younger and I knew less, I could sort of do it, but now I can't do it because
When you were younger, less experienced, and knew everything.
Yes, exactly. I had the Dunning-Kruger effect on my side. But now I'm just like, because there's, you know, you look at it a lot and you can't really say that much, you know? You can't, you know, you every other thing you want to say, it's not true. It's like, darn it, you know? So anyway, so this is how you develop a confidence interval around a measurement, right? There's another way to shake and bake this thing though. Right? This is a table. This is a tabulated t value, right? You can also develop what's called t experimental, right? Or t calculated. And that t calculated is your estimate of the difference between two values, right? And let's just say that these are the difference between two means, right? Pooled is it's like n1 times n2. I gotta figure this out. Hold on. Let's see here. Let's just go down here. F, blah, blah, blah. There we go. This is what we're doing. Comparison of means. So, yeah, here's S pooled. Yeah, n1 plus n2 minus 2. Right? And then this whole thing is square rooted. Right? And this gives you Oops, sorry. Oh, wait. What are you guys seeing? You guys are seeing the screen, right? You're seeing the PowerPoint now, right? Okay.
Yes.
Yeah.
Okay. So I'm gonna change here. So now, I'll go back to this stupid thing here. So we've got T calculated, right? Is the difference in the means times this. It's like a reduced degrees of freedom divided by S, right? So it's difference times N divided by S, right? And there's just kind of ways of aggregating the S values from the two measurements. So this is like, this answers the question. If you have distribution 1 and distribution 2, are they different? Oops, sorry. Right. So if you have like these values here and there, these will aggregate together. They'll give you X bar 1. These guys will aggregate together and they will give you X bar 2. And this is going to be N equals 6. This is going to be N1 equals 6, right? And so you could calculate, you could get a T value that's roughly proportional to the distance between those two mean values, or between those two averages. And that S, that T calculated, right? You would do, what you would do is you'd say, okay, you would try to answer the question, is T calculated greater than T tabulated? And T tabulated has a degrees of freedom, which is normally, this is going to be N1 plus N2 minus 2, and a percent confidence. Right? You're going to answer this question, is it greater, right? And if T calc is greater than T tabulated, then X bar 1 and X bar 2 are different. I got a good turnout eventually. Oh my Lord, we got 31 people. That's good. Amazing. So I better snap myself into shape here. So let's take a first of all, let's have any conversation that we'd like to have about this, right? Does anybody have any questions, or like would anybody like to insult my ancestry at this point? like a mother joke or maybe son of a dog or something like that. I don't know. Does anybody have any comments of that nature?
I have a question.
Yes.
Can you go back and read a part? I could not read what your handwriting was. I was really trying.
Uh-huh.
It's the T part is equal to the width in which 95% of probability, and then I didn't read that last word.
Oh, that is a combination of Sanskrit and ancient Egyptian. And what it's supposed to say is Lies.
Oh,
And so yeah, it's just
It's
like
the E.
yeah, just where it is, you know. Yes, sorry about that. Son of a dog. No, just kidding. I do not wish to insult my own mother. She was a nice lady, you know. But I don't know why I don't miss her so much. It's funny. I mean, I miss her a little bit, but she had a good life. I don't know. I don't know what to say. Probably reflects poorly on me. But anyway. Uh, so we'll use this next. We'll use this next. Just take a couple minutes, take a little breather, and then let's sort of refresh ourselves just for a couple minutes, and I'll be back at 8:15. Oh wait, no. All right, we have till 8:45, right? So I'll be back at 8:15, and then we'll go and we'll do examples for the rest of the period. We'll just work on the homework together because I've done like 5 of the homework problems or something. Pick 5 minutes. So if you want to do that, we can do that. Okay. So I will be back in less than 5 minutes, and think of questions and think of creative insults. I'm back. So, let's do some problems, shall we? So, let us say, this is from one of the homework problems. If you have 250 flu patients, you've got a friggin' disaster, but that's a different story. I mean, who would want to deal with 250 people with the flu, right? And the average temperature is 101.9 degrees. The sample standard deviation on this large sample is 0.7310 degrees. This is probably too many sig figs for 250 patients, but hey, whatever. So what is the fraction of the population? What fraction of this population has temperature greater than 103.65 degrees, right? Let's say what fraction has a really bad fever? That's one question we can answer, right? So in this case, what we would do is we'd say, well, let's calculate a z value, right? And z value is going to be x minus mu over s. Right? So this is going to be 103.65 minus 101.9 divided by 0.731. And this value will give us 2.394. Right? And then what we have to do with this datum here, we have to try to put that datum onto a universal distribution. So I'm going to switch out and then I'll switch back, okay? So what we need to know is what the critical value of z is, or what population fraction z equals 2.394 corresponds to, right? 2.39 is closest here to 2.4, right? So I'll jot this down. Z equal to 2.4. Area is equal to 0.4918. And in this particular form of a z table, the area increases as one departs from z equals 0. So this will go from 0 to 0.5 because this is sort of a half of this curve. And what we're going to do is we're going to go out to z is equal to 2.39. And we're going to ask ourselves, first of all, how much area is here? Oops, sorry. Let me go back here. we're going to say how much area, oops, is here, and then the actual question was how much area is over here in this corner. So basically, z is greater than 2.39, right? So what we can do, oops, this is 2.39, supposed to be 9. Right? So what we can do is we'll just go back to the this guy and say, well, that's 0.4918, right? So this is 0.4918. And so the total area on this side is 0.5000 and a 0.4918. That's something like 0.4918. Oops. 0.008. 2. So this is the fraction. So the fraction, oops, is equal to 0.82%. This is what fraction of the people will have that high of a temperature, assuming this is the distribution is normal. Does that make sense? Excellent. Good. All right. Casey speaks for everyone. Oh, good. I got other thumbs up. I love it. Cool. I got to get this stupid chat thing open. Oh, thank you, everybody. Okay, good. Okay, cool. Wait, there is a fire? What? It's raining. Yes, it is. Okay, sorry. I'm reading the comments. Okay, so next problema. Let's do a different type. Let us see here. See if I can decipher my notes. Okay. Let's go back to the homework here. So let's see here. This is bicarbonate. Population fraction, that's what we did. Okay. Okay, so we can do an F test here, right? So we can try to do this problem. And this is an exercise in patience here, because first we have to get through all this sort of contextual information, which is dubious, right? But kidney disease involves bicarbonate in blood. Normal bicarb is 23 to 29. Lab purchased a new instrument. You know, they took one sample, they measured it with both instruments. One gave 24.7 plus minus 1.5 Oops. Slightly different numbers. That's okay. I'm going to be using slightly different numbers here. I'm going to use 24.7 plus or minus 1.54 and 25.6 plus or minus 0.50, right? And the question is there a significant difference in the precision of the two instruments? So the way that one I can just summarize some information here. 24.7 plus minus 1.54 n equals 6. 25.6 plus or minus 0.50 n equals 6. So the first question on the table is, are the standard deviations different? And the way that one answers that is that you need to go to a table of critical F values, right? So in this case, the ratio of this is 1.59 divided by 0.5 squared, right? So let me just do that. 1.59. Yeah, that's 3. And if we square that, we get 10. We get 10.11, right? So I will write that down. But what we need to do is we need to look at this quotient and compare it to a table, a critical value of F here for n equals 5 and 5. So here's the F table, and 5 and 5 for this comparison of standard deviations, for this S1 squared over S2 squared, the critical value is 7.15, but the value that we got is greater than 10, right? So so these are 95% confidence F, and this is n equals 5 and 5, and that is equal to 7.15. Okay, so I'm going to switch us back over to Mr. Document Camera here. So this is 7.15, right? So and what we're going to do is we're going to take 1.54 divided by 0.50, square that value, and that is equal to this is equal to 8.13, right? And because 8.13 is greater than 7.15, we can say that the difference is significant. Right? And so this is I think that's it on this question. Right? It's just asking, are those differences significant? Let's look back at the question here. Let's look back at the question here. Yeah. Basically, it's just asking, is there a significant difference? So in this case, the answer would be yes. Does that make sense to everybody?
Oh yeah.
Okay, cool, excellent. So let's see here. Another problem.
Dr. Terrell, may you please go back to the show your work problem?
Sure.
Thank you, sir.
Absolutely.
I got it.
Okie dokie. So the next question that we're going to look at is we're going to calculate a t-value based on experimental data from a rainforest. Let's see. Oh yeah, no, here it is. Right. So in this problem, right, they're looking at the difference between N2O, nitrous oxide actually emitted from soil in a rainforest versus a plantation, right? And there's a, so what we'd like to do is we'd like to ask ourselves the question is the difference between 0.036 and 0.051, is this significant, right? And so 0.036 plus or minus 0.041, you can see that this standard deviation actually would cross zero. So like X bar minus mu would say that there's a negative concentration, right? So this is probably not a physical, well, it's definitely not, if you go negative in concentration, it's non-physical, right? So it's a serious question about whether or not this difference here between 0.036 and 0.051, whether that difference is significant. So let's go ahead and calculate the t-value for that difference. Right? So what we want to do is we want to do t calculated, and that's equal to x bar 1 minus x bar 2. I think it's an absolute value there, right? Times the square root of n all over s, right? Now, if we assume the population standard deviation for both sets is the same, right? That's one thing we're going to have to do here. And let's assume that that's 0.040, right? Let's say that S is equal to sigma is equal to 0.040, right? Then what we can do here is we can replace this guy with n1, n2 over n1 plus n2 square rooted, right? So we'll have t calc is equal to x bar 1 minus x bar 2 times n1, n2 over n1 plus n2, 1/2 over s, and x bar 1 will equal 0.051, x bar 2 will equal 0.036, n1 is equal to, oh gosh, what is n1? Gotta have that guy. N1 is 89 and 101, right? So, and then S is equal to 0.041. And if we just crunch this out, we get a T calculated is equal to 2.51. In my, using my numbers, your numbers will probably be slightly different, right? And the question is, at what level of confidence is this significant? And so we can say, we can look at the T table. I have a problem here because I'm looking at a T for 7 degrees of freedom, and the T value, the T table value should, looking one is N1 plus N2 minus 2. And this is going to be equal to, 190 minus 2 is equal to 188. And this is going to be, this T table value will actually equal the Z value for 95% confidence, or for whatever percent confidence we're looking at. So let's just look at this. So I'm going to grab a T value from the table here. Okay. I'll go to, here's T, right? And we have, it's like about 100 values, right? And so our degrees of freedom is really large, right? So it's between 60 and 120. You can see these values almost don't change here, right? 3.46, 3.73, et cetera. So we're going to ask ourselves, at what point is 2.51 on this table, right? And 2.51 is between 98 and 99% confidence, right? Okay, so this is 50, 90, 85. Okay, so I'm going to go over here, and I copied those values over. to here. So when we have a large degrees of freedom here, the 50% t-value is 0.67, the 90% is 1.1, 95% is 1.98, and 98% is 2.35. Our calculated value is 2.51, right? So our confidence in the difference is 98%. We can't say with 99% confidence that the difference is significant because that corresponds to a higher t-value than the one we measured. But we can say that it is 98% different. There's a 98% chance that the difference is real. So I will go over a couple more of these and I'll make a couple of short little videos. And then we can I'll show you how to do a couple more of the homework problems, and you guys can just sort of reproduce them and turn them in. This homework is actually due Friday at midnight. So it's actually a little more than I intended, but it's too late to change it because some of your classmates have already done it. Some who will not be named for their safety. Just kidding. So, that's all the time I have right now. Yes, sir.
Dr. T, I had a quick question.
Yeah.
On this question specifically, how do you figure out which standard deviation to use?
Right. Oh, okay. In this problem, this one. So it was actually it was stated in the problem. It's a very good question, right? Because you could use a pooled standard deviation or something weird like that, but it said in the problem to assume that the standard deviations given were population standard deviations. And so I used 0.040 instead of 0.041, but that small change in standard deviation shouldn't change the outcome. Does that make sense?
Yeah, so because of standard deviations, there's such a small difference between the two of them, it doesn't matter.
Right.
Okay.
Exactly. Yeah, it's just there's a very small difference. And if I wouldn't phrase it like that on an exam. I would make it very clear, like what, I don't like, there's too much ambiguity in statistics anyway, so I would try to make that very clear.
Okay, thank you.
Alrighty. So I actually have to hang up now, but I will be back at 12:30 to 1:30, or if you need additional time, you can email me and I will make time for you outside of those hours. Okie dokie.
Alrighty.
Dr. Terrell? Yes, sir.
Oh, may I just speak just for a few minutes?
Oh, I got your message. And okay. I will send you a Zoom link. Okay.
And I don't think I can meet during your office hours because I have work during that time, sir.
I know.
So
I'll send you a new Zoom link.
Okay.
I'll do it right
I'll
away.
meet you after class, sir.
Yeah.
Okay. Thank you so much.
All righty. Okie dokie. See you guys.
Bye, Dr. Terrell. I'll see you very soon.
Bye bye.